Welcome to a deep dive into nuclear fission, something I bet most people think is just physics.
Yeah, you'd think so, right?
Yeah,
But it turns out
it's not.
it's way more chemistry than you'd expect.
Yeah. So we're focusing on Lecture 10 of Innovations in Chemical Technology.
Yeah,
It was delivered by Professor Pushpito Ghosh at ICT Mumbai back in 2022.
that's the one.
And
Really fascinating stuff.
yeah, and we should say this is only part one.
Yes.
We're going to continue this in the next lecture.
Exactly.
So get this, the invention of nuclear fission, which you'd think is like, super important for nuclear science, is actually deeply rooted in chemistry.
Yeah.
Like, what?
I know, right? Most people don't realize that it wasn't physicists who were the first ones to really figure this out. It was chemists meticulously analyzing the results of all these experiments that, at the time, seemed to make no sense. It defied all the conventional wisdom.
So are we saying one of the most pivotal moments in nuclear science was actually like a chemistry problem?
Exactly. And this lecture really dives deep into that very aspect. We're going to follow the trail of research that led up to this invention of nuclear fission, highlighting the key players and their often unexpected contributions.
Okay, so Professor Ghosh starts off the lecture with a pretty bold statement. He challenges the whole idea of nuclear fission as a discovery. He's saying it's more of an invention
Interesting.
because human intervention was actually needed to trigger the whole process.
It's true. You don't just find nuclear fission happening out in the wild. It's not a natural phenomenon in that sense.
Right.
It really makes you think differently about how these scientific breakthroughs happen, doesn't it? It emphasizes how scientists are actively involved in manipulating and understanding the world around us.
Absolutely. So who are these like groundbreaking scientists that we're going to be hearing about?
Well, Professor Ghosh starts by introducing us to Otto Hahn. He was a chemist who won the Nobel Prize in Chemistry, kind of unexpectedly, for nuclear fission.
A chemist.
Yeah, a chemist. And he wasn't working alone. Lise Meitner, who was a physicist, played a crucial role, especially in explaining how so much energy is released during fission.
Okay, so a chemist and a physicist working together
Yeah.
to understand this incredibly powerful phenomenon.
And it's worth noting that Lise Meitner is facing, a lot of challenges because she was Jewish in pre-war Germany.
Right, of course. That was a very difficult time.
Yeah, it adds this whole other layer to the story. It highlights, I think, the often overlooked human element in scientific progress.
For sure. So how did this whole nuclear fission story even begin?
Well, Professor Ghosh kind of sets the stage, starting with Röntgen's discovery of X-rays back in 1895.
Right, X-rays. Everyone knows those.
Exactly. And then he moves on to Becquerel and his observations of natural radioactivity.
Oh, that's interesting.
Yeah. So Becquerel initially thought that these uranium minerals were absorbing sunlight and then re-emitting it as X-rays.
Okay, that makes sense.
But then he noticed something really weird. They were still emitting this radiation even on cloudy days.
Well, hold on.
Yeah.
So they weren't dependent on the sun.
Exactly.
They had their own internal energy source or
It
something.
was a huge mystery at the time. That's actually how the concept of natural radioactivity came about.
That's amazing.
And then comes Marie Curie.
Oh, of course, Marie Curie, the legend.
Right. Building on Becquerel's work, she isolated polonium and radium. These were elements that had far greater radioactivity compared to uranium.
Wow. So she was like going deeper into this world of radioactivity, trying to understand its building blocks.
Precisely. And it wasn't easy. Her dedication was truly remarkable.
I mean, Curie was incredible.
Oh, absolutely. She used a technique called fractional crystallization to isolate the radium from tons and tons of pitchblende ore.
What's fractional crystallization?
Basically, it involves dissolving and recrystallizing the ore over and over again, thousands of times, to separate the different elements based on their solubilities.
Oh, wow.
It's a painstaking process. Imagine doing that over 1,000 times.
1,000 times. That's insane.
Yeah. It really shows her incredible patience and dedication to science. I mean, it's hard to even imagine the kind of work that went into that back then.
Right. And without those efforts, who knows where we'd be today in terms of understanding radioactivity.
Exactly.
Okay, so we have Röntgen, Becquerel, and Curie. Who's next in this nuclear lineup?
Well, next up we have Ernest Rutherford, who used alpha particles to kind of unveil the structure of the atom.
Oh, Rutherford, the guy with the gold foil experiment, right? Like
Yeah.
shooting particles at a thin sheet of gold to see how they scattered.
Yeah, exactly. That led to the nuclear model of the atom that we all learned in school, with the tiny nucleus at the center and electrons orbiting around it.
Okay, so that's pretty basic stuff, but how does that tie into nuclear fission?
Well, Rutherford's work opened up this whole new world transmutation. It's the idea that you can actually change one element into another.
Wait, change one element into another, like lead into gold. That's like alchemy.
Haha. Not quite like that. But it was pretty groundbreaking. Rutherford achieved the first artificial transmutation by bombarding nitrogen with alpha particles. And guess what? He produced oxygen.
Whoa, hold on. So he was actually rearranging the fundamental building blocks of matter.
Exactly. It was a pivotal moment showing that the nucleus could be manipulated and changed. And that got scientists thinking, could they do the same thing with even heavier elements like uranium?
Okay, that makes sense.
But there was a problem. Alpha particles, which are basically helium nuclei, they have a positive charge, and so does the nucleus of an atom.
Right, right.
And as you probably remember from basic physics, like charges repel each other.
So the alpha particles were having trouble getting close enough to the uranium nucleus to cause any real change.
Exactly. It's like trying to force the same poles of two magnets together. They just push each other away. They needed a different kind of bullet, so to speak, something that wasn't repelled by the nucleus, something neutral.
I see. So they had the target uranium, but their weapon, the alpha particles, just wasn't cutting it.
Yeah, they hit a bit of a wall. But then, in 1932, three major discoveries rocked the world of physics. The positron, heavy hydrogen, also known as deuterium, and, most importantly for our story, the neutron.
The neutron, I remember learning about that in school. It's a subatomic particle, like a proton or an electron, but with no electric charge.
Exactly. And being neutral, it could penetrate the nucleus of an atom without being repelled by those positive charges. It was like finding the perfect key to unlock the secrets of the atom.
Okay, this is where things start to get really interesting. So who picked up this key and started experimenting with it?
That would be Enrico Fermi, an Italian physicist. He saw the potential of the neutron and began using it to induce artificial radioactivity in heavier elements, starting with iodine.
Wait, so he was making these elements radioactive on purpose. Why would he do that?
He was basically trying to understand how the nucleus worked, how these reactions happened, and in the process, he made another crucial discovery. Slowing down the neutrons actually made them more likely to interact with the nuclei.
Huh. So it's like if you throw a ball really hard at a target, it might just bounce off.
Yeah.
But if you toss it gently, it's more likely to stick.
That's a great analogy. And that principle is actually still crucial in today's nuclear reactors.
Wow. So he was not only manipulating these nuclear reactions, but also figuring out how to control them? That's pretty impressive. What did he do with uranium?
Well, being the ambitious scientist he was, he decided to bombard uranium with these neutrons, just like he did with iodine. He thought he was creating elements even heavier than uranium, transuranium elements, as he called them.
Hold on, so he's trying to create brand new elements that have never been seen before in nature. That's a pretty bold move.
Yeah.
But you said not everyone was buying it.
That's right. Some scientists were skeptical. They thought maybe he was misinterpreting the results of his experiments. And then a German chemist named Ida Noddack stepped up and challenged the whole idea of these transuranium elements head on.
What did she think was happening?
She proposed something radical. She suggested that maybe, instead of creating something heavier, the uranium was actually breaking apart into smaller fragments.
Wait, so instead of building up, she thought the uranium was actually splitting apart. That seems like a pretty huge leap in thinking. How did the scientific community react to that?
Let's just say her idea was met with a lot of resistance. It was just too radical for most scientists to accept at the time. It went against everything they thought they knew about nuclear physics.
That makes sense.
Even Irene Curie, Marie Curie's daughter,
Yeah.
and her collaborator, Savitch, they stumbled upon some evidence that seemed to support Noddack's idea. They found a substance from their own uranium experiments that behaved like lanthanum, which is a much lighter element than uranium.
Okay, so there was some evidence out there.
There was, but they hesitated to really challenge those accepted theories.
I guess it's always hard to be the one to go against the grain, especially in science where everything is supposed to be based on evidence and established knowledge.
It's true. It can be really tough to shift those long-held scientific paradigms, even when you have some evidence that points in a new direction.
So what happened next? Did anyone pick up on Noddack's idea and run with it?
Well, Noddack's idea may have been initially dismissed, but the seeds of doubt had been planted. And as we'll see in part 2 of this deep dive, those seeds would eventually sprout into a full-blown scientific revolution. So we left off with Ida Noddack's, kind of revolutionary idea, right? That uranium, when you hit it with neutrons, might actually break up into smaller pieces, not creating these heavier elements like Fermi thought.
Right. And even though Curie and Savage, they found some evidence that seemed to kind of back up Noddack's theory, the whole scientific community just wasn't ready to accept something that, radical.
Yeah, it was just too big of a leap at the time.
So where did things go from there?
Okay, well, this is where Otto Hahn and his team at the Kaiser Wilhelm Institute in Berlin come back into the picture.
Hahn, the chemist?
Yes, remember, a chemist, not a physicist. And he was known for being super, super meticulous and precise in his analytical work.
Got it. So he's going back to basics, like really carefully looking at what exactly was going on during these uranium bombardment experiments.
Exactly. They were particularly interested in this one substance that was produced during the bombardment. It seemed to have a half-life of 3.5 hours.
Okay, half-life. I vaguely remember that from high school chemistry class.
Yeah, it's the time it takes for half of a radioactive substance to decay, basically. But anyway, this substance, it kind of acted like radium.
So their goal was to isolate it and figure out what it was.
Precisely. And this is where Hahn's expertise as a chemist really shines. They used classic techniques like fractional crystallization and co-precipitation.
Could you break those down a bit? Some of us, haven't spent a lot of time at a chemistry lab.
Sure. Imagine you have like a mixture of salt and sand, right? You could separate them by adding water, dissolving the salt, and then pouring off that salt water, leaving the sand behind. Fractional crystallization and co-precipitation work in a similar way, using the subtle differences in how soluble different elements are and their chemical behavior to separate them from a mixture.
Ah, so it's a like super fine sieve, but instead of separating by size, they're using chemistry.
Yeah, that's a great way to think about it. And for a while, it seemed like things were working, like they were separating the mystery element from the barium, which they were using as a carrier.
Carrier.
Yeah, just something to help with the separation process.
Got it.
But then they ran into a problem.
What happened? Did their methods just, stop working?
Well, no, they could separate other elements from barium without any issue, even radium.
Okay.
But this mystery element, which they thought was radium, it just wouldn't separate from the barium, no matter what they did.
That's weird. So their techniques were working, but this one substance was just stuck to the barium.
Exactly. And that's when that aha moment hits. Hahn realizes that if they can't separate this mystery substance from barium, even after purifying it over and over again, it must mean that it's not actually radium at all. It's barium.
Hold on. So what they thought was radium, something heavier than uranium, was actually barium, something way lighter.
Precisely. The only way that could happen is if the uranium atom was actually splitting apart into these smaller pieces.
Wow. So after all this super careful analysis, they stumbled upon this incredible idea that uranium was actually splitting.
Yeah. It was a huge shift in thinking.
But how did they know for sure it was barium?
Well, Hahn and his team were really thorough. They wanted to be absolutely sure, so they bombarded their samples with actual radium, which they were then able to successfully separate from the barium. This proved that their techniques were sound and that the mystery element was indeed barium.
It's crazy how a seemingly simple chemistry experiment, just trying to separate stuff, led to this monumental discovery.
Right. And it really makes you wonder what Noddack thought when she heard about these results.
Yeah, she must have felt vindicated.
Professor Ghosh doesn't actually mention Noddack's reaction, but, I'm sure it was pretty satisfying to finally see her theory confirmed after being dismissed for so long.
For sure. But, finding out that uranium could be split, that's just the first step, right? I imagine understanding the how and why and what it all means, that's a whole other level.
Absolutely. This was just the beginning.
So where do we go from here?
Well, we'll dive deeper into all of that in part 3 of this deep dive.
So we've gone from mysterious radioactive rocks to, literally splitting the atom.
I know, right? It's mind-blowing.
It is, and it's all thanks to a bunch of chemists who weren't afraid to, challenge what everyone thought they knew.
Exactly. They weren't afraid to think outside the box.
And what I find really interesting is that this whole discovery of nuclear fission, it wasn't just about, equations and experiments, right?
No, not at all. There's a very human side to this story.
It's about collaboration and perseverance, even exile, with Lise Meitner having to flee Germany and still continuing her research.
Yeah, she never gave up.
It makes you realize that scientific progress, it's often driven by these individual stories, by people overcoming these incredible obstacles to, pursue knowledge and try to understand the world around us.
And in the case of nuclear fission, that pursuit led to a discovery that would completely change the world in ways that, we're still grappling with today.
Right, and that's what I keep coming back to, that this discovery has such profound implications, both good and bad.
It really does. I mean, think about it. Clean energy, medical breakthroughs, but also, nuclear weapons. It's a lot to take in.
It is. It's like this incredible power that comes with a huge responsibility.
Exactly. And that's what makes this lecture so thought-provoking. It leaves you with this sense of awe at the power of the atom, but also this, this urgency to think carefully about what it all means.
It reminds us that scientific discoveries, they don't exist in a vacuum, right? They have these real-world consequences that we can't ignore.
Absolutely. They affect society, politics, everything. So does Professor Ghosh offer any guidance on, how to navigate this complex landscape?
He does. He reminds us that the responsibility for using this power wisely, it doesn't just fall on the scientists who made the discovery. It's on all of us.
Right. We all have a role to play.
It's a call for informed decision-making, open dialogue, and I think just a deeper understanding of what nuclear fission is really all about, the good and the bad.
I agree. And it's a message that feels especially relevant today, with all the challenges we're facing. Climate change, energy security.
Yeah, for sure.
The story of nuclear fission, it's not just some, historical anecdote. It's a reminder that scientific breakthroughs often come with these really tough choices, and that as a global community, we have to face those choices head on.
So where does all of this leave us at the end of this amazing deep dive?
Well, I think it leaves us with a few things. A deeper appreciation for the power of science, just the sheer curiosity that drives it. And I think a better understanding of how complex the process of discovery really is.
Yeah.
And probably most importantly, a sense of responsibility. We have to make sure this incredible power is used for good, for the betterment of humanity.
I think that's a great way to put it.
And the conversation doesn't end here. Professor Ghosh picks up the story in Lecture 11, going deeper into, what happened after this discovery.
I can't wait to hear what he has to say.
But until then, I think it's up to all of us to, keep asking questions, keep learning, keep thinking about the role of science in shaping our world.
I agree. It's been a fascinating journey through the world of nuclear fission.
Yeah, it really has.
And I think we've only just scratched the surface.
Exactly. There's always more to learn.
Thanks for joining us on this deep dive.
It's been a pleasure.
And we'll see you next time for another exciting adventure into the heart of science.